Hello, welcome to Bedroom Builds at the From Python to Rust series, episode D, files, continuing from the previous episode where we talked about operator overloading. This episode will be fairly short because all I'll be giving is a short introduction in how to read text and binary files and how you can assemble a file path. All the rest that you can find in the nice documentation of Rust and Python, because file operations is a really vast topic with lots of different things. I try to do the idiomatic way of both languages. With this, you have a good starting point. The rest is then up to you and the documentation. I will jump over to our code. First example, on the left, as usual, we have Python spread out in a way so it matches more or less what's happening on the right in our Rust code. Starting with Rust, since we are learning this all new, we have to import the standard file module at the very top, and then we also do import standard IO. The self here is actually importing IO for us, which is very useful because down here we are using IO, and with the curly brace list we get to also then import the buff read and the buff reader. Buff read is a trait necessary to do the line reading, and the buff reader is a buffer that will not have us read the whole file into memory and then split it or something, but it will be efficiently reusing a buffer to do the operation. So main function is returning an IO result. This is just a short helper that you can return an IO error from your function, and this is our return type. Since we don't really return anything meaningful from main, we use this empty parentheses notation. Then the first line, we are using the fully qualified standard environment arguments and collect them into a vector of string to get the command line arguments. And then down here, I just hard coded first argument to be the file name coming in. So we are using the file module open to open the file. Below, we are creating our buff reader instance. The idea of the loop coming up is to count instances of a certain string. Therefore, we have to initialize the counter that I call the found with 0. Then below, we use the buff readers feature to give us lines back. Then this will actually be a result. So this can fail potentially because the buffer can run into allocation issues or the file goes away or some other error. So that's why I use the question mark that I also used up here to open the file. And this will in both cases be an IO error, and therefore up here the IO result can deal with this. The question mark, as explained in the error handling episode, is returning the error for us in case of an error. Otherwise, it actually gives us the value inside the OK. And then we use the line that we have found to be OK, split it with the comma, collect it into a vector of strings, and on the second column we have the target where stuff was shipped from the sale in our CSV document. We match this to Tanzania, and we try to figure out how often something was shipped to Tanzania. At the very bottom we have the output. Same as on the left in Python. This is much less code because most of this is built into the library. It's very easy to do command line arguments, so you just use sys.argv. If you use open this way, it by default assumes the file is a text file. Therefore, the context manager that gives us this file handle allows us to iterate directly, or actually it's a generator, I think, to generate directly loop over the lines in the text file. So we take advantage of this feature. Then we split our lines, and we then also filter by Tanzania, do the count, and make the output. This, in both cases, is of course code that is already written, so you would find really powerful and amazing CSV parsing libraries in Python, and the same is true for Rust. but this is an easy way to show how this can be done. Now let's run these things and check how these two perform comparatively. I have prepared a shell for this. So let's first check out the documents that we have. This is a free download of some generated data. So this is not actual sales data. This is generated random stuff. It comes in a compressed 7Z file, and it's 1.5 million sales records. Let's look at the head of the CSV to get an idea of what's in there. So you can see here, it goes region, country, item type, all kinds of other things in the header. And then there's already a delivery to Africa, and again Africa, then Oceania, then Europe, Slovakia, and so on. 1.5 million lines with random items and delivery dates and all this other stuff. And we are, here is actually Tanzania, so we are trying to find out how many of those lines were actual sales that went to Tanzania in the end. Then I wrote a small script that does a benchmark for us. What does this one do? So first it uses the word count tool to read it into our operating system's file system cache. Then I reuse the macOS time feature to also give us information of how much memory is being used. So you can see all of this here is the word counting. Then here I use the time binary with this LP feature flag. Then I run the Python with the optimized flag, our simple code in with the CSV, and the same with the optimized binary coming out of Rust and with the same records thing. This is of course not a scientific benchmark, but should give us an idea of what's happening. Let's run the benchmark. Great. The first output that we see here at the very top line is the word count that runs for us to get it into our operating system files cache. Then below we have the output of the Python library. It tells us there are 8,136 sales for Tanzania, and the same is true in the Rust code, so the counts are correct. The real time is a bit faster for Rust, but that's likely some side effect or whatever. So you can see that Python is actually very efficient when it comes to text file reading. And the bigger difference that you can see though is here we are using close to 1 megabyte of RAM. But here we are using 5.6 megs of RAM. And that's a very good sign, because as I showed before, the document is 100 megabytes and something big. So both codes are actually fairly efficient and not reading the whole file into memory and then doing operations on it. It really goes line by line, not using a lot of space. Here the reason is of course the Python interpreter. This is a bit bigger than binary that's compiled for the operating system. But otherwise, performance is very similar, and that's kind of the way you should be processing stuff, if possible, when it comes to text. Let's hop over to the other code that is about binary file reading. Now, here is a combination of showing off two things: how to read a binary file into memory this time, and what to do with file paths. From Python 3.5 onwards, you have the pathlib that allows you to do path manipulations that are very powerful, and also some important and easy to use file reading features. So I'm using that here in the Python code. I created a function that will return the bytes from a file in the most efficient way that I would know right now in Python. So byte array is going to be returned, and that is based on the bytes read from this path object. Then the main function will be similar to the stuff that we've seen already. We get the file name from the first argument. We run our byte file thingy. Then we print out the length of the binary bytes that have been read. And then we use the path module to give us the home directory. Then we path join from the home directory onwards a subdirectory called library, and in there is another directory called fonts. And with this, we then print out if we found those two directories. And right below, we try to see what happens if we pass a directory to our file reader. And this will be our last operation. The same is done on the right in Rust. For this, we import again the standard IO, because this will be used for the IO errors. Then we also have a similar module that provides you path and path buffers to do the modification of your paths in a cross-platform way. First function implemented is, as on the left side, the bytes from file. The first interesting thing here is the argument. And as we've learned in the episode about traits, you can actually give trait bounds for your arguments. And in this case, the trait bound is the sref trait for a standard path. This means that you can pass anything where the sref to return a path has been implemented. This makes it much easier for yourself and your users of your libraries to use your function, because you do not have to call toString or sstr or path new or some other constructors to pass something to your function, because this will actually get a reference to a path object, and this has been pre-implemented for static strings, for actual heap strings, for path buffers, and all kinds of other fancy cool stuff. And this way it's much easier to use from a programmer's perspective. Then we return again an IO result. This time this will be a vector of U8s, so byte vector. And here we are using a function that luckily was implemented by the standard library. So we have in standard FS something called read that will simply read the contents of the whole file. Question mark again is doing the error handling if it comes up. In the main function, we also return an empty result again. Get the arguments. First argument is passed, and here is the advantage, right? This is actually a vector of string. I am giving a reference to the second element, and the compiler is happy with what I'm passing in. It doesn't have to be a path, and therefore I don't have to do some conversion magic calling this function. I just pass in my reference, and the rest is done with the trait that has been implemented for, in this case, a reference to a string element. Then we also print the data's length, and below we have the idiomatic way of how to get a hold of the home directory. So we have to use a crates.io module, a crate for that, called the dirs. Inside there you have the home dir function that will give you a home directory or might fail. So that's why I'm using expect here. And then we are using also the path system, so path new based on our path buffer. And then we join again the library directory, and inside the library you have the fonts directory, and we have that here. And lastly, we also try to see what happens if we read from this thing. Let's hop over to our shell where we can compare those two running. Let's hope this works on the small screen. So I'll clear the screen. I will show you again the files we are talking about. So we have now the 33 mega 7-zip file. This is a binary file, so we read this one. And before we passed the 180 megabyte sales records. We have the second benchmark, if you will. This time we are doing a useless line count on the binary file to get it into the operating system's cache. And then we call it with Python, and after that with the Rust version. Let's see how that goes. Okay, we can see that in both cases, the runtime is very similar because, yeah, 0.10, 0.3, something, it's very fast. It's probably some side effect and not really Python versus Rust. However, the memory usage is vastly different. So here we have 75 megabytes of RAM usage for the 30-something megabyte file, as you remember. And here it is 35 megabytes of RAM usage. So that is a lot more efficient. Otherwise, we get an error from our Rust application that tells us that it is a directory and cannot read from the file. And up here we get our bytes. Let's scroll up a bit to see what happens in the Python version. So it also tells us the byte size, and when we try to load our fonts directory and count and load the file as a binary, it will also fail, telling us that this is a directory, giving us the full stack trace back. Works very nicely. This was a short introduction on how to do file management in Rust. The main takeaway is that you should always make sure that arguments for your file handling operations using this implements sref path pattern. This makes it much easier for other people to use your functions, and even if it's only yourself that will be using it, it will make it much easier for yourself as well. Thanks for watching. Coming up next on the From Python to Rust series will be testing.